Welcome back to the deep dive. Today, we're tackling a paradox that I think is haunting the hallways of every major AI lab right now.
Mm.
It's a problem of success, really. We've reached this point in, 2026, where the reasoning models, the successors to OpenAI o1 and DeepSeek R1, are effectively geniuses.
They really are. They've become incredibly proficient at logic, at math, coding.
Right. They're scoring in the 99th percentile on almost every test we can throw at them. But here's the snag, and it's one that keeps researchers up at night. If you have a classroom full of geniuses and all you have is a stack of worksheets designed for third graders, what happens?
They get bored. They breeze through it.
Exactly. And more importantly, they stop learning. We are literally running out of questions hard enough to teach these models anything new. It's you guys call the data ceiling.
That's right. Specifically in the realm of reinforcement learning with verifiable rewards, or RLVR, we are hitting a wall where the models are just too smart for the training data we have.
So the solution seems obvious, right? Just go write harder questions. Go hire 1,000 PhDs in quantum physics to write these baffling no problems. But the paper we're looking at today says, no, don't do that.
It says that would be a huge waste of time and money.
Instead, this paper, and it was published just yesterday, February 13th, 2026, by researchers from Tencent and HKUS, proposes something that sounds, well, it sounds almost like cheating. They say we should take the easy questions,
Right.
the garbage data that we usually just throw away because it's too simple, and just glue them together.
Literally compose them. Yeah, like snapping Lego bricks together.
And their claim is that by doing this simple gluing trick, they can make smaller, more efficient models that actually beat the massive billion-dollar Goliath models.
It's a classic work smarter, not harder moment
Yeah.
for AI training.
Okay, I want to be skeptical here because that sounds way too good to be true. Just glue easy stuff together and get genius results. We have to unpack that. But before we get to the solution, let's really understand the problem. You mentioned RLVR. For everyone listening who isn't a machine learning engineer, can we just strip the jargon? What's actually happening?
Sure. So let's distinguish this from how, say, ChatGPT used to be trained, which was mostly predict the next word. RLVR is different. It's active. It's like a pop quiz.
Okay.
The model gets a problem, usually math or code, and it has to generate a solution. The system then checks that solution. If the answer is right, the model gets a reward signal, little thumbs up. If it's wrong, thumbs down.
So it's trial and error.
It's exactly trial and error. The model tries, gets feedback, and adjusts its internal wiring to get more rewards next time. But here is where we hit what the paper calls the Goldilocks problem. The difficulty has to be just right.
Because if it's too hard.
If it's too hard, what we call solve none prompts, the model fails 100% of the time. It never sees a thumbs up. It's just flailing in the dark, and it learns nothing because there's no signal for what success even looks like.
That makes sense. If I tried to read a book in a language I don't know at all, I wouldn't learn the language. I'd just be staring at a page.
Precisely. But the paper focuses on the opposite problem, which is actually more dangerous right now. Solve all prompts. These are questions the model gets right 100% of the time.
Now, hold on. In the real world, if I get 100% on my test, I'm popping champagne, I've mastered it. Why is that bad for an AI?
Well, you've mastered it, sure, but are you learning? I mean, if you're a calculus student and I give you a worksheet of 2 plus 2, you'll get them all right. You'll feel great.
Yeah.
But your brain isn't forming new neural pathways.
I'm just retrieving what I already know.
Exactly. And in machine learning terms, this is catastrophic. We talk about the gradient. The gradient is essentially the gap between what the model knows and what it needs to know to solve the problem.
Yeah.
If the model already knows the answer perfectly, the gradient is 0.
So the signal to the brain is just a flat line.
It's a flat line. The model updates nothing. You are burning electricity, running these massive GPU clusters, generating heat, all to tell the model, good job, for something it could do in its sleep. It is completely wasted compute.
That is a wildly inefficient way to run a business, let alone a supercomputer. Did the researchers quantify how bad this waste actually is?
They did. And the numbers are honestly startling. They were training a model called Qwen34B, a solid mid-sized reasoning model, and they found that within just 50 training steps, which is, that's the blink of an eye in a training run, the ratio of solve-all prompts jumped to over 50%.
So half the data became useless almost instantly.
And it eventually stabilized around 75%. That means for every 4 questions in your data set, 3 of them were effectively waste paper. The model had graduated past them, but we just kept feeding them to it anyway.
So we have a huge shortage of hard data, and this brings us back to their solution. Composition-RL. You called it Lego bricking. How do you take two waste questions, two easy things, and turn them into something that actually creates that learning gradient?
It's a methodology they call SPC, or
Right.
sequential prompt composition. And it's, deceptively simple. Imagine you have two separate easy math word problems. Let's call them question A and question B. The model can solve both in a millisecond.
Okay, question A, question B, both easy.
Right. Step one, you take question A. Let's say the answer to question A is the number 7. You rewrite the problem slightly. So instead of just asking for the answer, you define a variable. You say, let variable X be the answer to this problem.
So you're creating a placeholder. X equals whatever the solution to A is.
Right. Step two, you go over to question B. Let's say question B asks you to calculate 5 plus 1. You find that number 1 in the text, you rip it out, and you replace it with a new variable, y.
Okay, so now question B is broken. It has a hole in it. Calculate 5 plus y. You can't solve that without knowing what y is.
Exactly. And step 3 is the glue. You create a rule linking them. You add a sentence that says variable y is equal to variable x minus 6.
Ah, I see the chain forming. To solve question B, I need y. To get y, I have to apply the rule to x. And to get x, I have to solve question A.
You've created a dependency chain. The paper gives a really concrete example in Figure 1. They take a simple algebra problem about finding a sum of values and a second problem about simplifying an expression. By linking them, the model can no longer just memorize the answer to problem B.
Because the input for problem B changes depending on the answer to problem A.
Precisely. And the model has to maintain the state of the problem. It has to solve A, hold that number in its working memory, apply the transformation rule, and then plug it into B. It turns a retrieval task into a real reasoning task.
But I have to play devil's advocate here. If question A is easy and question B is easy, isn't doing them back to back still, easy? It's just easy plus easy. Why does this actually challenge a genius model?
That is the core skepticism, isn't it? And it's a great question. Why isn't it just busy work? The answer lies in error propagation and rigor.
Rigor.
Think about it. If you have a 95% chance of getting A right and a 95% chance of getting B right, your chance of getting the whole chain right is lower.
Yeah.
But more importantly, it forces the model to be honest. In a single question, a model might hallucinate a step but then stumble onto the right answer by luck.
The stopped clock is right twice a day effect.
Exactly. But in a composition chain, if you mess up that first step, if you get X wrong, it is mathematically impossible to get the final answer right.
Yeah.
The error creates a domino effect. So the feedback signal becomes extremely sharp. It punishes fuzzy thinking much more severely than isolated questions ever could.
So you're raising the stakes. You can't think your way through the middle steps because the end depends on them entirely.
Correct. And the beauty is you can generate these chains infinitely. You could take your data set of 10,000 easy questions and combine them in different pairs, different orders, with different linking rules. You suddenly have millions of hard problems without writing a single new line of math.
You're recycling the waste data into high-octane fuel. So, does it work? When they trained models on this Frankenstein data, did that solve-all percentage actually drop?
Drastically, yeah. On a subset of the math data set, the solve-all rate, the waste rate, it dropped from about 81% all the way down to 41%. Suddenly, the model was sweating again. It was being challenged.
That's a huge efficiency gain right there. But the ultimate test is benchmarks. Does this actually make the model smarter at new problems or just good at solving these weird linked puzzles?
The results suggest it's genuine intelligence gains. They tested this on models from 4 billion all the way up to 30 billion parameters. On the AMY 24 benchmark, which for context is a high-level math competition that stumps most humans, the gains were significant. But the most interesting finding was something they called the curriculum strategy.
Curriculum, like how we teach kids in school.
Exactly like that. This is a crucial detail. They found that if you just throw the double chain problems at the model on day one, it struggles. It's too much, too fast.
Like tossing a first grader into calculus, they just give up.
Right. So they used a staged approach. Phase 1. Train on the normal, easy questions that let the model master the basics. That's depth 1.
Okay.
Once the model hits that solve-all plateau and stops learning, then you switch to phase 2. Depth 2, the double-linked questions.
You increase the weight on the bar.
And when that plateaus, you go to depth 3, 3 questions chained together. This ordering matters. You can't skip the steps.
It's progressive overload. It's exactly like weightlifting. You don't start with the heaviest weights, you build up to them.
And this progressive overload approach produced the best results. In fact, a small Qwen 3.4b model trained with this curriculum actually outperformed an 8 billion parameter model, a model literally twice its size that was trained with other state-of-the-art methods like AlphaRL.
Whoa, that's a real David versus Goliath moment. A model half the size winning because it trained smarter. That has to be terrifying for the company spending billions on bigger and bigger chips.
It proves that we haven't hit the limit of these models' intelligence. We've just hit the limit of our teaching methods. We were letting them slack off with easy homework.
Now, up until this point, we've been talking about math. Math A plus math B. And that makes sense. Logic flows neatly in math. But there was a section of the paper that really threw me for a loop. They didn't just stick to numbers, did they?
No, and this is where I think the implications get really wide. They asked, is this just a math trick or is it a general reasoning trick? So they built a new data set called physics math composition.
Very literal naming convention there.
Very. They took physics problems, calculating velocity, force, mass, and they glued them to geometry or algebra problems. So it'll be like, solve this physics scenario to find the velocity, then use that velocity as the radius for this circle to find the area.
Okay. So mixing domains. And I assume that made the model better at both physics and math?
It did. It beat out the standard training methods by a wide margin. But here is the shocker. Training on these composed math-physics prompts improved the model's performance in completely unrelated fields, specifically law, engineering, and chemistry.
Whoa, wait. You're telling me that solving a velocity problem helps an AI answer a legal bar exam question. How does that even work? There are no vectors in a contract dispute.
It seems completely counterintuitive. But think about what the model is actually doing when it solves a composed problem. It isn't just memorizing formulas. It's practicing the act of conditional dependency.
Conditional dependency.
It's the structure of, if A is true, then B happens. And if B happens, then C must be the result. That logical structure, that scaffold, is the exact same whether you're calculating the trajectory of a ball or determining liability in a lawsuit.
If the defendant was not present, A, then the contract is void B. It's the same muscle.
It's the same muscle. We often think of knowledge as the bottleneck. Does the AI know the law? But this suggests the bottleneck is actually reasoning depth. By training it on these physics chains, you're forcing it to hold complex, multi-step dependencies in its head. You're building the reasoning muscle, and that muscle works just as well in a courtroom as it does in a lab.
That is incredibly cool. It suggests that reasoning is a transferable skill for AI, just like it is for us. Learning Latin might help you code, not because Latin is code, but because they both require this rigorous structure.
Precisely. And it validates the idea that we might not need a massive law data set to teach legal logic. We might just need really complex chain structures of any kind.
I want to pivot to one last technical piece because I think it explains why this works so well. The paper mentioned something called implicit process supervision. Now, usually when we talk about supervision in AI, it's about a human checking the work. But you said earlier, we can't hire 1 million mathematicians. So how does this solve that?
This is the real hack that makes the whole system viable. In traditional RL, we have a black box problem. The model spits out a long chain of thought and a final answer. We check the final answer. If it's right, we say, good job.
But we don't look inside the black box. I mean, it could have made 2 mistakes that just happened to cancel each other out. It could have just guessed.
Right. Ideally, we would use process supervision, checking every single step of the logic. Did you carry the one? Did you divide correctly? But checking every step requires massive human effort, or these very expensive reward models.
Enter composition-RL.
Enter composition-RL, because the problem is constructed as a chain. Problem 1 leads to problem 2. The structure itself acts as a checkpoint. Remember our variable
X and Y.
Right. If you get problem 1 wrong, you recover the wrong variable x. If x is wrong, it is mathematically impossible to solve problem 2 correctly. So simply by checking the final answer, you are implicitly guaranteeing that the intermediate steps were also correct.
So you're getting the rigor of step-by-step checking, but with the cheapness of just checking the final answer.
It's implicit supervision. It's brilliant. The paper actually plotted this out. They showed a graph where as the model got better at the final answer, its accuracy on that hidden intermediate variable, V1, went to near 100% in perfect lockstep.
It forces the model to be honest. It can't hallucinate its way through the middle because the end completely depends on it.
It aligns the incentives perfectly. You just can't cheat the chain.
So let's zoom out. We've covered the solve-all problem, the Lego solution, the David beating Goliath results, and this crazy cross-domain transfer to law. The researchers went to depth 3, 3 questions chained together. Where does this end?
That is the provocative final thought here, I think. If combining 2 simple tasks teaches an AI to think for 30 seconds, and combining 3 tasks teaches it to think for a minute, what happens if we compose 100 small tasks?
100. That's not a test question anymore. That's a project.
Exactly. I mean, think about writing a novel, or coding an entire operating system, or designing a microchip architecture. Those aren't single hard questions. They are thousands of simple tasks. Write a sentence, define a function, check a dimension, all chained together in a very specific logical order over a long period.
So you're saying composition RL could be the path to what people call long horizon reasoning.
It's very possible. If simple composition acts as a curriculum, we might be able to train AI to handle projects that take days or even weeks just by training them on longer and longer chains of simple prompts. We don't need to find a write a great novel data set. We just need to chain the write a sentence data set effectively.
That is a staggering thought. It turns the complexity of the world into just a really, really long sequence of simple things.
Which, I mean, if you think about it, is exactly how humans solve big problems. We break them down into little blocks and we snap them together.
Well, on that note, I'm going to go look at my to-do list and see if I can compose my laundry, my emails, and my grocery shopping into some complex reasoning task. Maybe if I link them together, I'll actually get them all done.
Just make sure you verify your rewards. Don't eat the cookie until the laundry is done.
I will try my best. Thank you so much for guiding us through this. And to our listeners, thank you for diving deep with us. It really changes how you look at easy work, doesn't it? It's not just busy work. It might be the raw material for brilliance.
Absolutely.
See you next time.